Hello everyone, thanks a lot for the nice introduction, and welcome from my side as well. Myself, I have a background in photonics. In fact, during my research years, I spent quite some time doing ultra-fast spectroscopy and terahertz spectroscopy experiments. And that is why today here at Zurich Instruments, I am responsible for the optics and photonics application realm. So in today's session, we'll be taking a deep dive into the approaches we can take advantage of to master periodic signal analysis for optics and photonics applications. I would like to start first by motivating why it is important to recover proper signal recovery in optics and photonics experiments. Well, in a way, the reason is quite simple. Optical measurements can unlock the highest measurement precision, arguably the highest precision achievable nowadays. To support this claim, I brought you here two examples. On the left-hand side, we have the very famous LIGO experiments, where researchers measured gravitational waves by means of an interferometric measurement, and they were able to resolve tiny length changes on the order of 10 to the minus 21 meters. On the right side, we have one of the first attosecond laser pulses measured in the lab of Ferenc Krausz that pushed the time resolution down to the attosecond, so 10 to the minus 17 seconds. Notably, for this work, Ferenc Krausz was awarded the Nobel Prize in Physics last year. In the end, regardless of the specific application, the challenge is always the same. Once the signal is measured, is captured, and converted to the electronic domain, the challenge is to preserve its information content. And this is where us, Zurich Instruments, come into the game. So our mission is to provide best-in-class dynamic signal instrumentation for advanced research and development labs. And how do we do that? Well, our approach is to take off-the-shelf hardware with adequate specifications in terms of speed, sensitivity, noise, and combine it with a software infrastructure that allows the user to benefit from efficient workflows, compelling APIs, intuitive user interfaces. And with this approach, we're also able to add features to the instrument over time, thereby increasing their value. Zurich Instruments, we have four specific instrument pillars. We have the quantum computing control systems, so for qubit readout and analysis, lock-in amplifiers, Boxcar Averagers, and impedance analyzers. Who is doing that? So here at Zurich Instrument, we are more than 160 people now, coming from more than 25 different countries. The headquarters are here in Switzerland, where I'm also sitting at the moment, but we have offices scattered throughout the world: USA, Korea, China, France, Japan, and India. Since 2021, we are owned by Rohde & Schwarz, but still independently running our business. Now about today. So what kind of questions can you expect to be addressed in today's webinar? So we will start by understanding the principle of lock-in amplifiers and why are they useful on a broader level in optical experiments. Then we will see how certain instrument settings can affect the measurement result. And then we will introduce another technique, Boxcar Averaging, and compare it to lock-in amplification and see where the two techniques differ and when one might be more advantageous than the other. All of this will be supported by application examples, both for linear spectroscopies. We will see two very interesting examples of how lock-in amplifiers are used, and then pump probe-based spectroscopies, where Boxcar Averagers play a very significant role. At the end, I will also like to share with you some useful pieces of advice, some tips on how to set up and run the best optics and photonics experiments. Now, a key question. So what are the effects we are generally interested in when we are running a photonics experiment? So we might be interested, for example, in linear absorption, so transmittance of simple transmittance of light through a sample, and see how this light is transmitted or reflected from the sample. We might be interested in the polarization state of our laser beam, for example, and this is a very typical case in terahertz spectroscopy, where the information about the terahertz fields are encoded into the polarization of our laser beam. Then we might have some induced transmissions or absorption changes, and this is very typical in the pump probe spectroscopy, when you have multiple pulses that excite the sample, and you want to look at how these pulses are absorbed and transmitted. Otherwise, also we might have gains, so pump pulse gains or Stokes pulse gain, as this might be the case in stimulated Raman scattering spectroscopy and microscopy. Now, once we know which effects we want to measure, what are their sizes? What are their typical sizes? Well, I think nowadays in the most advanced optical experiments, is a very common requirement to be able to measure effects down to relative amplitudes down to the 10 to the minus 6, 10 to the minus 7, but even lower, 10 to the minus 8. And generally, these effects need to be measured either on top of large backgrounds, and this, for example, can be the case when we are measuring the Stokes gain in our stimulated Raman scattering experiments. So we need to measure a small change on top of a big pulse, a big background. Or otherwise, we might need to measure our signal that is completely buried below the noise floor of my measurement. And this can be also with a simple absorption experiment, where the absorption of my sample is really, really small, maybe because the concentration of my sample is very low, and I need to be able to extract this signal from the noise background. Again, the challenge is always that we need to be able to extract the information content from our signals. The information we are looking at when we're running an experiment can be of different types. We can have, for example, an amplitude change for a certain time duration, where we want to measure both of these things. We might have a sinusoidal modulation, where we want to measure the amplitude and the phase of this modulation, maybe with respect to another signal. Then we might have pulsed signals. This is very common nowadays with ultra-fast maybe experiments, where we want to measure some parameters of this pulse train, for example, the intensity or the pulse width or other type of parameters. But in order to understand how to define if a measurement is good or not, we need a metric that helps us define the quality of such a measurement. And generally, this metric is called the signal-to-noise ratio. And the definition is rather straightforward. So it's basically simply the ratio between the signal in terms of its average divided by the noise in terms of its standard deviation. This is the linear definition of signal to noise. What is very common also is the logarithmic definition of the signal to noise that is measured in decibels. So in order to qualitatively understand what's going on, what does this mean, we can have, for example, here an example where I plotted two different traces with two very different characteristics. We can see, for example, starting from the blue trace, that the value of these measurements are quite spread out around the average value, meaning that the standard deviation is rather large. So instead, for the orange curve, we have that the measurement results are very, very close to the average value, having therefore a much lower standard deviation. And so you can clearly understand this signal to noise as how spread out are the values of our measurement around the average value. As you can imagine, for this very example, the signal-to-noise ratio of the orange trace is better than the one of the blue trace. And this for this specific case, we had a factor of 10, that 10 dB, so decibels, that corresponds to a linear factor of 3. Now, how do the typical experiments look like? I think 90, maybe 100% of the experiments can be actually broken down into 4 functional parts. We have the laser source. We have the source, sorry. This can be a laser, can be an LED, can be a lamp, can also be sunlight. We have the experiment where everything is designed and engineered to address the parameter of interest. Then we have the detector, crucial element, that basically takes our optical signal and transforms it into the electronic signal. Then we have the signal analysis chain. And I think that I dare to say that the signal analysis is sometimes, I would say, overlooked part of the experimental setup. Overlooked in the sense that it's many times underestimated how much improvement can lead a proper signal analysis of the signals that we are looking at. But anyway, before making any measurements, we need to understand the noise sources in our experiments and in our system. Here on the right-hand side, I have a very typical frequency noise spectrum, where the most common contributions are highlighted. Starting around DC, we can see like a noise contribution that is increasing as we approach the 0 frequency. This is called 1/f, or pink noise, and it, in fact, it approaches DC proportional to the inverse of the frequency. Then, moving to higher frequencies, we have the white noise floor. And in general, for optical experiment, the white noise floor is given by the shot noise of the detector. And it many times represents the best case scenario in terms of noise performance of our measurement. So if we are limited by the shot noise of our detector, it means generally that we are in a very good place. Of course, then there are also some spikes. Like these very famous ones, typicals are the 50-60 Hertz of our power lines, or radio and mobile a bit at higher frequencies. Now, a very common way of counteracting, very common approach to counteracting noise is averaging. Averaging is equivalent to low-pass filtering around DC. And this is already making things better because, of course, we are filtering out the noise at higher frequencies. But as you can see, we are basically doing a low-pass filtering around the point where the noise is the highest. If we were to picture this in our optical experiment, this would probably look something like this. We would have our source that goes directly into the experiment. The signal is then detected, okay? And then, transformed into electronic signal, and this electronic signal is then digitized, so directly digitized and averaged. Now, how can we make things a bit better here? The idea is that if we now add a modulation into our experiment, what we are effectively doing, we are shifting our signal of interest from DC to higher frequencies, specifically to the frequency of the modulation that we have applied to our experiment. Then, after we have modulated our light, our signal, we need a way to demodulate it, and this is usually done with lock-in amplifiers or Boxcar averages. Which are the most common kind of modulators that we can find for optical experiments? Well, there are many different types, and which one to use depends a bit on the frequency range that we wanna achieve. We can start by very classic mechanical choppers, where the light is mechanically blocked by a spinning wheel. And the frequency range achievable by these devices is of the order of tens of kilohertz. And then, if you want to move to higher frequencies, up to tens of gigahertz, we need to resort to a more complicated device like acousto-optic modulators or electro-optic modulators. Alternatively, there is also, of course, the way of using pulse laser system, so for example, mod lock laser, that are naturally modulated at the repetition rate of the laser itself. Now we have our modulation. What we need the right instrument to demodulate our signal. Now here, the easy thing would be, Zurich Instruments and local amplifiers are the best, but this is not the point I want to make here. Of course, the most important parameter to choose the right instrument is the signal input bandwidth. And this signal input must be generally higher than the modulation frequency we want to look at. The thing is, like in modern digital instrumentation, there is much more than just a lock-in amplifier. There are more ingredients that might be interesting to run a more optimized experiment. For example, there can be a large range of low-pass filter constants, or it can be like large dynamic reserve, so it tells us how good is my instrument to reject noise. Or there might be also other tools that might be interested for my experiment, as for example, oscilloscope integrated directly into the lock-in amplifier, sweeper, the possibility of demodulating the same signal at multiple frequencies, for example, first harmonic, second harmonic, and so on, and also maybe the possibility of running a Boxcar Averager measurement onto the same device. Here, so at Zurich Instruments, we have instruments for any frequency needs. So starting all the way down from DC up to 8.5 gigahertz, so up to the microwaves. With the latest two addition to our portfolio, the GHFLI and the SHFLI lock-in amplifiers. Now we have already introduced lock-in amplifiers in a way, but how do they actually work? So the principle of operation of a lock-in amplifier is rather simple. The idea is that we have a lock-in amplifier needs two signals. It needs the signal where we want to measure and analyze, right, our input signal, and then it needs a reference signal at, let's say, our modulation frequency. And this reference signal, for example, can be the sync signal coming from the chopper. The lock-in takes these two signals and mixes them. And effectively, this mixing is like a multiplication, so it multiplies these two signals. Then the result of this mixing is run through a low-pass filter. And this low-pass filter is simply a series of cascaded RC filters. After the filtering, in output, what we get the amplitude of our signal and the phase of our signal with respect to our reference. The transfer function of a lock-in amplifiers can be thought as the one of basically of a band pass filter, where our center frequency is arbitrarily choosable, that is the modulation frequency, and also the bandwidth of our filter can be adjusted. Now, I want to mention that in modern digital instrumentation, and of course all Zurich Instruments lock-in amplifiers, all these operations here are performed in the digital domain. So there is no analog components inside our instruments. This has a lot of advantages, and of course, for example, also the fact that for low-pass filtering, there are not actually physical RC resistors and capacitors inside the instruments, but rather all this filter are simulated filter thanks to digital signal processing technique. Now here with this I would like to jump to the very first application of today, and I really like this application because it shows how much you can do with just single instrument for many aspects of your experiment. The application is called Tunable diode laser absorption spectroscopy, TDLAS for short. TDLAS is one of the most common technique that is used to analyze the properties of gases and, for example, concentration, temperature, flow velocity, or other parameters. And this is usually done by measuring the wavelength-dependent absorption of light through the gas medium. As the name already suggests, we have it employs a source, a tunable source, a laser diode, whose wavelength can be swept depending on the driving signal that we apply to it. When the wavelength of the light matches one of the absorption lines of the gas, of the species that is inside our gas cells, the photodetector records a reduction in the light intensity. Now, when the concentration of the gas is maybe ultra low, so there are very few molecules that contribute to the absorption of light, the signal is extremely small and very hard to detect. What is usually done to increase the sensitivity of this technique is to add a small sinusoidal modulation to the driving signal of to the laser diode, and this basically has the effect, as we have seen before, to shift our signal to the frequency of this modulation, thereby increasing significantly the sensitivity of the measurement. Now, of course, after the photodetector, the signal needs to be analyzed with the lock-in amplifier. Now, once the signal is recorded and analyzed, we need to understand how can we optimize the signal-to-noise ratio of our measurement. Before answering that question, though, I would like to show you another application example. And I think this is a really an amazing example of how, again, one single instrument can help you analyze a signal in so many different ways. In this work, researchers wanted to analyze the composition of microdroplets inside a microfluidic chip. The experimental setup, they had this microfluidic chip where these droplets were running through it, and they were excited by 4 different lasers at 4 different wavelengths, and whose intensity was modulated at 4 different frequencies. The fluorescence signal was then detected by a photomultiplier tube and then sent to our HF2LI lock-in amplifier that was able to basically analyze the signal in parallel at all these 4 wavelengths. So the information of this, the fluorescence of the microdroplets was collected in parallel. And I think the results are quite exciting. If we look at the graph here on the bottom, we can see, so time is running on the x-axis, and we can see some peaks, and these peaks basically correspond to the presence of the microdroplets in the focus of our laser light. And you can also see different colors in these peaks, so the contribution of different fluorescent dyes to the emission of the micro droplets. And as you can see that all this information can be easily collected with one single instrument and in parallel. This is nice because basically now what one can do can identify the droplet population based on their fluorescent fingerprint and assign them, let's say, a place in the fluorescence space, sorry. Now, again, we see all these peaks and we can see how they are very nice and sharp and well resolved, but how can this how can we then optimize the SNR to have these nice peaks, these nice looking peaks? So the main knob we can turn is the time constant of our low-pass filter, or alternatively, equivalently, I should say, the measurement bandwidth of our low-pass filter. I think many of you might be familiar with low-pass filtering, that the characteristic of a low-pass filter is defined by the cutoff frequency. That is basically that frequency where the signal power is attenuated by 3 dB, and this is basically inversely proportional to the time constant. Here on the bottom of the top plots, we have both the time domain and frequency domain response of filters with different bandwidths. As we can see, as we decrease the bandwidth of our filter, we are making of course, the measurement bandwidth narrow. And this basically means that we are letting through less and less, fewer and fewer frequency components, meaning that we are able to reject more noise. At the same time, though, the price to pay is that we need to basically wait more. As we decrease the bandwidth, we need to wait longer for the filter to settle to the new value. And I want to mention that this is a physical trade-off that one needs to make. There's nothing to do with the instrument. This is how the physics of the low-pass filter works. Now, in general, the measurement bandwidth, so it should be as narrow as possible in order to filter out as much noise as possible, but at the same time also support all signal components. to better visualize what I mean here, I have an example of the same peaks analyzed with 3 different bandwidths, filter bandwidths. Starting from the very left, we have a rather large bandwidth, where yes, we can see the peaks, but we can also still see a lot of contribution from the noise. If we go to the very right, we now see, if we now reduce the bandwidth significantly, we can see that now the noise has disappeared, but at the same time also the peak have smeared out. Meaning that some information that actually makes up, some frequency information that actually makes up these peaks has also been filtered out by the filters. In the middle here we have, for this specific experiment, the best trade-off between these 2 bandwidths, where basically we can see both peaks very nicely and resolved, and also the noise is relatively good, rejected. The second knob we can turn to affect our signal-to-noise ratio is the filter order. Now, the filter order simply means how many filters, how many low-pass filters with the same bandwidth I'm cascading after one another. Again, here on the top, we can see the effect of different filter orders. On the frequency domain, we can see that as I increase the filter order, what is happening is that the roll-off curve of my filter steepens out, meaning that we are getting closer to what is more like a brick wall filter type. Again, the trade-off for this steepening of the roll-off curve is that the signal will then need more time to settle to the new value, meaning that if you want to make an accurate measurement, we need to wait longer time. So, for these reasons, the filter order in general should be kept as low as possible to minimize the settling time of our signal, but at the same time ensure the suppression of all frequency components, spurious frequency components. I would say that the filter order is a very nice tool to use when we have, for example, a noise component that is very close in frequency to the frequency of our signal. And again, to show you what I mean here, I've brought you an example where we have filter order equals 1 here on a certain signal. And as you can see that there is some sort of ringing, okay, some interference on top of the signal that we wanna measure. If we now increase the filter order to 6, we can clearly see that this interference has been removed, meaning that this interference frequency component was very close to our signal, and thanks to the steepening of the curve of the filter, we have been able to suppress it. Okay, so now I would like to switch the focus a little, and I would like to introduce a set of techniques that are nowadays very popular in many optics and photonics labs. And these are the pump probe based spectroscopies. Now, pump probe spectroscopy has become very popular nowadays, thanks to the advent also of amplified ultra-fast laser systems. And this is because when we have an ultra-fast laser and we run a pump probe experiment, the time resolution of my experiment is only limited by the width in time of my pulse. So if we have attoseconds or femtosecond pulses, we can really push the resolution of our experiments down to 10 to the minus 15 or 10 to the minus 18 seconds. The setup for a pump probe spectroscopy, basic setup, let's call it, it's rather simple. We have a pulse laser that is split into 2 branches. One of the branches is modulated and delayed. Then the 2 branches are again collimated again together, and they co-propagating, they impinge on our sample. The first pulse, usually the pump pulse, creates some sort of photochemical process that is then read out and analyzed by a time-delayed probe pulse. The signal is then usually analyzed and resolved with a lock-in amplifier or a Boxcar Averager. Again, as I mentioned, the nice idea, the thing is that since we have the 2 pump probe pulses are time delayed, one can reconstruct a full dynamics of the photochemical process of the sample. Now, as I mentioned already, we have these techniques have become extremely popular, and that is why there is a lot of variation from the same let's say, basic setup, you can find a lot of variations in literature here. Here I've brought you 3 examples, not an exhaustive list by any means, but just to give you an idea of the popularity of this kind of technique. We have usually we can have a more classic, so to say, visible pump and near probe experiments, or maybe we are having more like visible pump or terahertz probe experiments. We want to study terahertz transients from our samples, or also imaging applications where pump probe is used to acquire images in microscopy. Now, as said, many times pump probe spectroscopy are used in combination with ultra-fast laser sources. Many times, ultra-fast laser sources, amplified ultra-fast laser sources, are running at very low repetition rates. And this means that the signal that we are looking at looks something like here in this plot here. So essentially, we have that the signal we're interested in is confined in very short amount of times, in very short pulses. And I think also intuitively, what one would like to do with this type of signal is to measure only where the signal is present, so around the peak, and ignore all the rest, because after all the rest is simply noise. And here is where the Boxcar Averager comes into play. As we've seen before, for the lock-in amplifier, what we are doing, we are taking our signal and multiplying it with a sinusoidal reference. In the case of Boxcar Averaging, instead, we are taking our signal and multiplying it with an arbitrary square wave with arbitrary duty cycle. After the multiplication, we have an integration stage where basically everything under the high time of our square wave is integrated and then sent to, again, a low-pass filter. That in this case is no RC filter, but rather a simply moving average filter, meaning that a certain amount of this type of integrated boxes are averaged, and then the result is then output out from the instrument. Now, in order to understand why and when Boxcar averaging can be advantageous for this type of signals, let's go back to our signal, exemplary signal that we've seen before. If we now were to take the Fourier transform of such a signal, what we end up with is something like this in the frequency domain. As we can see, the signal power is then distributed across many different harmonics. Now, if we were to take a lock-in measurement of such a signal, what we are effectively doing is measure just the signal at the one single harmonic, ignoring all the information that is present in all the other harmonics. Instead, if we now start to box our signal with our Boxcar Averager and we decrease the time of the gate of our Boxcar function, we can see that we are extending our frequency detection up to higher frequencies, thereby including also the information in these harmonics that previously was ignored. How large are we increasing our bandwidth? It depends on the time, the gate time in the time domain, inversely proportional to the gate time in the time domain. Now, I think from this picture you can clearly understand why Boxcar averaging for certain type of signal can be very advantageous, because it allows you to integrate and recover the information present also at higher harmonics. Of course, it's also true that if there is no information at higher harmonics and we were anyway to run a Boxcar Averager measurements, we would basically integrate only the noise present at the higher harmonics if no information was present there. Another very interesting and important difference between lock-in and amplifiers and Boxcar Averager is the filter function. For the lock-ins, we have that the signal setting is nonlinear, exponential, and it depends on the filter bandwidth and the filter order. For the Boxcar Averaging, instead, we have that the settling is completely linear and only depends on the amount of boxes that we are windows that we have averaged, and there is no correlation between among previous prior data points. Now, a very, let's say, an application that makes heavy use of Boxcar averaging is terahertz time domain spectroscopy. And this is very dear to me because I've spent quite a lot of time during my PhD performing such experiments and using Boxcar averagers. So the idea here of these experiments is that we want to create some terahertz pulses, terahertz transients, and investigate our samples with this, let's say, low frequency terahertz transients. The setup is very similar to a pump probe setup we've seen before. We have the ultra fast lasers that is basically split into a pump part where the terahertz are generated. Then the terahertz pulses interact with the sample, and in order to detect this interaction, it's generally used a second beam coming from the same laser that with a technique called electro-optic sampling. And the very nice thing about this is that with terahertz, one is able to actually recover directly the electric field of the interaction. Again, in the subset of terahertz spectroscopy experiments, there is also a lot of variety, as I have shown you here. There can be linear terahertz experiments, Kerr effect experiments, but also two-dimensional terahertz, two-dimensional Raman terahertz experiments. So there is a huge variety among all this type of experiments. The next application that I would like to share with you is actually something where the researchers compared the two measurement approaches we just discussed, lock-in amplification and Boxcar averaging. And the application is some stimulated Raman scattering microscopy. The researchers in the paper, they had a fiber laser that was a 40 megahertz repetition rate that was split into two branches as usual. One of the two branches was modulated at half repetition rate of the laser, so at 20 megahertz. The beams were then recombined and sent to objectives into their microscope. Now, in order to compare the two approaches, what they did, they took some imaging of some beads, polystyrene beads, and what they did, they basically said, okay, let's try to achieve the same signal-to-noise ratio with both techniques, and let's see which one of the two techniques needs the least amount of time. And what they found out is that for this case, Boxcar averaging was leading to a pixel dwell time. So for each pixel of this picture, the dwell time was half with respect to the one of the lock-in amplifications. And this is good. This is not because, of course, not only reduces our measurement time by half, which is always something we aim for, but also reduces it avoids maybe the photo damage when investigating delicate biological samples. Okay, so now we are here. We've seen a lot. So what have we learned? What is the summary of what we've learned today? So we've seen two different measurement approaches for the analysis of periodic signals. Lock-in amplification. We've seen that lock-in amplifiers are extremely good tools to recover signals that are buried into the noise, thanks to their ability to measure the signal that is shifted in frequency with respect, for example, to DC. And we've seen two nice examples of TDLAS spectroscopy and the fluorescence at multiple wavelengths, where the signal was made up of many different frequencies, and one single device could easily recover all of them at the same time. Then we've introduced Boxcar averaging, and we've seen that this type of approach can be extremely helpful when we're dealing with low duty cycle signals. And this is often the case when we are, for example, dealing with experiments in pump probe spectroscopy, where ultra-fast lasers are very commonly used. Okay, now I would like to finish, as I promised, with some pieces of advice that I reckon important when trying to run the best optics and photonics experiment. The first thing is that before running the actual measurement, before exploring what we want to look for a sample of in our experiment, we need to characterize the noise in our setup. For example, relative intensity noise of the laser, detector noise spectrum. We need to understand these noise sources and gain insights which are the least, so the less and the more noisy frequency regions in our system. Then, once we've understood this, the idea is that we need to choose the modulation frequency as high as possible in order to be sure to be in the white noise regime, and of course away from potential noise sources. Additionally, for example, for pulsed laser experiments, modulating at half repetition rate of the laser, so basically this is the highest modulation frequency one should use, minimize also the correlated, so the shot-to-shot noise fluctuations of our laser sources. Then, of course, once we've detected our signal, we need to select the best measurement approach based on the characteristics of that signal. Low duty cycle, high duty cycle. And this is hard to do sometimes a priori. And the only real way to understand which is the best measurement approach is actually by comparing the signal-to-noise ratios of the different approaches, as for example, lock-in amplifiers and Boxcar averages. In this way, once we know which one is leads to the best signal-to-noise ratio, we can make an informed choice. Then, always needs to be sure, we need to always evaluate and assess the trade-off between noise rejection and signal dynamics. Meaning that we need to adjust the filter setting, of course, in order to achieve as much noise suppression as possible, but making sure that we are not filtering relevant information on the signal, on the dynamics of our signal. If unsure, one should use multiple measurement bandwidths to check which one is the better one. Now you see these you might see these 4 tips and say, okay, but this, I mean, I need to have a lot of instrumentation. This increases a lot the complexity of my system. But the truth is that in Zurich Instruments lock-in amplifier, you can perform all these tasks within the same instrument. For example, with our UHF-LI lock-in amplifier, you can absolutely characterize the noise, measure the RIN of your laser. You can analyze the same signal with different tools simultaneously, as for example, run the lock-in amplification and Boxcar averaging and compare directly, side by side, the signal-to-noise ratio. You can demodulate at multiple frequencies, as for example, it was the case with the fluorescent at multiple wavelengths. You have plenty of range in terms of measurement bandwidth, so you are making sure that you are not cutting any of the relevant information from your signal, and you're also able that you're rejecting as much noise as possible. And this brings you, what kind of benefits does this bring you? It brings you reduced complexity in your setup, better results, higher quality results, and of course, shorter time to publication. With this, I am finished, and I would like to thank you for your kind attention, and now the field is open for questions.